cloud. Screen. It's not that important. If you don't want to write it, it's okay. Just trying to know who's here. All right. Okay. Thing is okay. Right. Well, thanks everyone for coming today. I should probably talk about what happened yesterday for a second. So yesterday was my fault. I'm sorry. There was I didn't understand that you could these Zoom addresses, like you can, or these Zoom meeting numbers, like I thought you can only use them on like the day that you reserve the Zoom lecture for, the time for, but it turns out you can use them any day. So I actually put together a new meeting on Wednesday, and I sent it to Professor Eager, and I forgot to send it to you guys, which was really stupid. So that was my fault. Did anybody get a chance to watch the makeup lecture? Robin, no? I did. You did? Okay. What, you're Lucas? Tyler, it's okay. Okay. Amelia?
Are the makeup lectures posted on YouTube or with cross website? The links I found on the
Oh, no. Okay.
That has me mind.
So they're supposed to get put onto YouTube. I don't know if that one got put onto YouTube or not. Neil Jenkins is supposed to do it. I guess he's the IT guy, the IT whiz. So he was supposed to do it. I don't think he did it. Yesterday. You saw it on Zoom? Yeah. Okay. So Amelia, you weren't able to open it up on Zoom?
Oh, I didn't try. I just tried the YouTube link. Sounds interesting.
What did I send you guys? I thought I sent you a Zoom link, right?
I think I only had Zoom.
Well,
I think there was a, like, way back when there's a link that's supposed to be where everything is
Right.
at some point, which I think is YouTube, but like last week it wasn't.
okay. This is a mess. I'm sorry. This is second law thermodynamic stuff. Okay, so I'm going to kind of backtrack a little bit. I'll discuss a little bit kind of short about what we talked about yesterday, just so everybody's up to date, everybody's together. Since you obviously can't ask questions from YouTube or from the Zoom video, if you want to talk about any of this stuff, you can email me. My office is right across the hall. It's 4.142. You can come talk to me. I'll be there the rest of today pretty much. I will be probably be in that office twice a week. So Professor Eager and I are trying to like solidify when the recitations are going to be. Like it's going to be on this day, Tuesday every week. And I'll be on campus that day for the recitation. So if you want to come talk then, that's fine too. Okay. Okay, so I'll start then. The main point here is in order to get the lightest, most efficient structure, you need to focus on geometry and materials. You can't just focus on one like most companies do. Forget the other one. You'll never get to the most optimized design if you only focus on one, but you have to focus on both. Yesterday, I showed you guys this example here, two identical useful sports cars. Track toys, they're about the same size. The engine's about the same size. They're both made out of aluminum extrusions, except one is about 450 pounds lighter than the other one. And the difference is that the extrusions, rather than being welded together, were glued together on the lighter car. So the yellow car, they were welded together, and the silver car, they were glued together. And the result of that was that there was no heat effect zone. So when you weld aluminum, you get a weak area adjacent to the weld. In order to compensate for that, you make the wall thicker because stress, it's force divided by area. So to make the area bigger, the stress goes down. And this didn't. Yeah.
Oh, I didn't want to interrupt you.
No, go ahead.
I was going to ask if there was a difference in the type of absorption or something like that. Very much impact.
Right. The Lotus actually has a fiberglass crash structure. It's like a Formula One crash structure in front of it. So Lotus doesn't actually rely on the tub to absorb energy in a crash. But I don't know what they did on the Renault. But the glue is pretty darn good. And the reason it's pretty good is because it's taking up such a large area. You're trenching that load over a big area because there's lots of glue, right? So you can distribute that load over a bigger area, reduce the stress concentration, and there's still good strength and energy absorption. They do put rivets in there in case there's a fire, right? Because the glue would melt or burn off, actually, not melt, burn off. So they do put a couple of rivets in there. So we were saying that the difference in weight is attributed to the fact that in the yellow car, they had to take that thicker section and carry it through the whole body structure in order to make everything strong enough, which means they had a lot of superfluous material, which is what drove the weight up. The most important properties for reducing weight are probably these two here. So stress, specific stress, which is stress divided by density in this case, and then Young's modulus or stiffness constants divided by density. The bigger these values are, the more efficient potential you have of making a lighter structure with the material, the material that has these. We talked about systems engineering. We talked about Cyril Smith. We said that materials are, or he said that materials are really just systems with hierarchy of subsystems, and you have to optimize the whole set of systems in order to get the material that has the highest specific strength and specific stiffness. We talked about the fundamental paradigm of material science, so the processing, structure, property, performance relationships. This going back to the 50s and 1950s, this was really kind of a thing of scientists. They thought about processing, gives you the structure, gives you this property. They moved from your left to your right. Okay. Later on in the 80s and 90s, the engineers started to say, how can we actually design materials rather than just taking what's in a book, looking at a table of values? How do we actually design materials to achieve certain strength, stiffness, fracture toughness? How do we actually design materials? And that is moving from the right to the left. We talked about the Materials Genome Initiative. Thank you, President Obama. This is a government's recognition that materials by design is a real thing. And the government has provided funding and resources and support to create databases, thermochemical databases, to pay grad students to develop models for predicting the links between the processing structure and the structure of properties. So big effort, lots of money, and the goal is to reduce the amount of time to develop new materials. We talked about CalFat, that Morris Cohen and Professor Wagner here at MIT, morning, and it's good. Professor Wagner and Morris Cohen and I'm just forgetting the other guy's name. Sorry, this guy here, Larry Kaufman. These people developed computer simulations and modeling that would allow you to draw phase diagrams. For anyone who doesn't remember, phase diagram is sort of like a map of temperature versus composition. You have this composition at this temperature, you have this phase. Phase might mean it's face center cubic or body center cubic or some combination or HCP. We talked about how the Steel Research Group at Northwestern University kind of took a lot of this to the next level to engineer new steels, high strength steels, high toughness steels that were used in the main bearings of the space shuttle, and also to build lighter weight landing gear for fighter aircraft that are landing on jets, landing on aircraft. And we talked about the term computational materials engineering and integrated computational materials engineering. Computational materials engineering is developing models that run off computer simulations on high-powered computers to predict what happens at the different links in the fundamental paradigm of material science.
Dr. Baskin, if you're updating the slides, the screen slides aren't updating on the Zoom.
They're not?
They're not.
They're not. Wow. Okay, let me try again. Okay, here's screen.
Sometimes they freeze.
Thank you for letting me know. How's that? Is that?
Yep, it is updated now. Thank you.
Okay, I apologize. So
No worries.
this is so irritating. Okay, so I'll get it right eventually, guys. So these are what we were showing before. I think Sam, you saw these yesterday.
Correct.
These
That's
updated
kind of how
now?
Yep, it's updating now. It looks good. Thank you.
Okay, right. So, okay, so CME, computational materials engineering, computer models, thermochemical databases that run those models to predict what's going to happen during the different links, the processing to structure and structure to properties links. ICME, the I, I'm personally a little confused with, depends who you talk to. A lot of people talk about the I being the ease with which the input outputs from the various models can feed into different models, and whether you have to, if there's a lot of human intervention to go in there and change formats and things to get to different computer models to read the output from previous models. Okay, we talked about the Olsen diagram. So this is a different type of representation of the processing structure property performance relationships. This is a way of incorporating Cyril Smith's philosophy of systems, a hierarchical systems of systems and subsystems, all working together to optimize the properties of the material. And on the far left there, these are the processes. These can be various different steps of the process. These can be mixing chemicals. These can be deoxidizing, taking sulfur out. These can be solution treating, quenching, tempering, etc. All the different processes you might do with a material in order to achieve the structure. And the structure is the one in the center. There can be many different features that make up a material structure, a hierarchy of subsystems. So there's atoms, there's interstitial atoms, there's precipitates, there's grains. We talked about inclusions a lot last week or yesterday. These structural subsystems work together to provide a system of properties. The properties that are most interesting to us right now that we're going to focus on this class to maximize lead weighting are the specific strength and the specific stiffness. And we're going to focus on the structures that get us those, and then the processes that give us those structures. So back to this one. So the first thing we're gonna focus right here on strength to density. Later we'll talk about stiffness to density. And a good first pass to find a material that has the best specific strength properties is to look at the Ashby diagram. So this is a graph or a map of specific strength versus density. You're looking for materials that are in the upper, I screwed this up last time, the upper left corner, or close to the upper left corner. The closer you can get to the upper left corner, upper left-hand corner, the higher the strength to density ratio, the highest potential for that material to make a lightweight structure. Goal setting is important. You can't just go, you can set rational goals for how you can design a material to achieve a certain level of properties. Okay, you can't make wood that has a 10 gigapascal yield strength, that's impossible. But what you can do is you can look at existing materials and you can understand, like if this material has a high strength and this material has a high toughness, and there's this component, this subsystem of the microstructure that's giving you the high toughness in one material, and then in the second material, there's this other subsystem that's giving you the high strength. Can you then make a material somehow that's got both of those microstructural features and potentially have high strength and high fracture toughness? That's really designing materials. Here are some examples of the microstructural subsystems. Okay, there's atoms, right? We all know atoms, right? There are lattices of atoms. There's dislocations. Dislocations a missing column of atoms. There are little needles and things sometimes with steel, the Lath-Martensen. There are precipitates, both aluminum and the higher strength steels can strengthen via precipitation hardening. There are stringers, manganese sulfide sunk the Titanic. I always tell people that. We talked about that last time, that back then when they made the Titanic, they didn't really understand the deleterious effects of sulfur in steel, and so they didn't purify it out of the steel, and as a result, they got these manganese sulfide stringers. And then this makes the steel brittle, especially at low temperature. So when the Titanic hit the iceberg, it was cold. They had a brittle fracture, and then all those side plates that contacted with the iceberg opened up and let in all the water, and then things sunk. It's interesting, a couple of years, well, during World War II, there's another story. During World War II, the Navy had a bunch of ships made called the Liberty ships. And I guess they either didn't know or cheaped out on the steel, and they had a lot of sulfur stringers in the steel. And if you guys go online and you Google Liberty ship, you'll see that ships that literally cracked in half, like sitting at a port like in Lake Superior, just literally cracked in half right down the middle. Anyone seen those pictures? They're pretty scary. The ships literally cracked in half, and they had built probably hundreds or maybe thousands of these ships, and they would crack in half because the steel they used had too much sulfur in it. Another system subsystem of microstructure is are grains. Okay, anybody who's polished up a piece of aluminum or steel or brass or even titanium and then etched it, looked under the microscope, and seen these grain structures. I think it's a lot of fun to look at those under a microscope, and if you guys would, maybe you would, hopefully you would. Then we talked about grain boundaries. We talked that grain boundaries kind of span a number of different length scales, right? Because if you have 10 micron grains or 1 micron grains, then you can think of having miles and miles, actually kilometers and kilometers of grain boundary. But in one dimension, they're only ancients thick. In the other direction, it could be, like I said, meters or kilometers long. We then talked about dislocations. Okay, so dislocation is a missing column of atoms in a lattice, and they account or they explain why metals, for example, are not as strong as their theoretical strength. Because if you look at the calculation that shows like how much energy does it take to pull 2 atoms apart, and then you sort of expand that and see what's the strength of this material based on that energy to take these atoms apart. Materials should be a hell of a lot stronger than they are. Okay, so the reason for this is that materials actually don't deform that way. They actually fail that way. They have these things called dislocations, these missing column of atoms. These missing columns of atoms are able to move across the lattice, move through the lattice when they're applied when shear load is applied to the lattice. Okay, and they move, and that takes a lot less energy to move a dislocation than it does to separate atoms. So that's why materials aren't as strong as they theoretically should be. But it also gives us an ability. It gives us an ability to design a material that would be stronger, because if you can find a way to make it require more energy to move this dislocation through the lattice, that's really strengthening. That's really what the essence of what strengthening is. So most of the research and work and grad students slaving away has been about trying to find ways to increase the energy to move dislocations through the lattice. Strengthening mechanisms. At the end of the class yesterday, we began to go through some of the strengthening mechanisms. These strengthening mechanisms are designed to make it more difficult for dislocations to move through the lattice. We talked about work hardening was the first one we spoke about. So if you take a paper clip and you bend it a couple times back and forth, you'll notice it gets a little bit harder each time to bend it. And what's happening there is that as you bend it, the dislocations, some are moving and they're tangling up on each other, so they can't move any further because they're tangled up on one another. And even worse, like as you do this, there's new dislocations that are formed as you're bending it. So there's more and more of these dislocations piling up on top of one another, stopping each other from moving. And that's strengthening. It always surprises me that there's like kilometers of dislocation line in a lattice, in a metal that's been deformed like that. When you think about like a little cube, maybe centimeter by centimeter by centimeter, there's like a kilometer dislocation line. It never ceases to amaze me. There's an equation shown here that relates to increase in strength with the dislocation density, and some other variables there, grain size and so forth, to tell you, to predict what the strengthening is associated with work hardening. We also talked about, yesterday we talked about substitutional strengthening. If you have a lattice of atoms, say they're all the same, called the solvent, and then you can replace some of these atoms with a new atom. That's called substitutional strengthening. Sometimes the atoms, if they're small enough, they'll fit between the solute, so the thing you're alloying it with. Sometimes they're small enough that they don't sit in the interstices between the atoms. And that's another way to stop dislocations from moving. When you get a little atom and you stick it between other atoms, it causes what's called a lattice distortion. And that lattice distortion increases the energy required to move dislocations through the material. There's been studies done on if you have this solvent material and you put in this solute, can you predict whether it's going to sit at a lattice site, or can you predict whether it's going to sit in an interstice? And there's a lot of modeling that's been done around this, and I think there's some general rules of thumb out there about percentage of the atomic radius. I think the rule says that if the radius of the solute is within 15% of the radius of the solvent atom, then it will sit in a lattice position, a substitutional outlet. If it's smaller than that, it'll sit in between. So it turns out that when they sit in between the atoms in the interstices, they actually increase strength more than if they occupy a lattice position. Steel is a material Steel is a material that is strengthened through interstitial. So the little carbon atoms sit in between the iron atoms. Brass is a material where the solute occupies a solvent position in the lattice. Okay. Precipitation strengthening is very important. I think this is one of the most effective ways to strengthen a metal. 6061 aluminum, 7000 series aluminum, 2000 series aluminum. These materials are all precipitation strengthened. Okay, there are some steels, some really high performance steels that are strengthened by this mechanism. The danger in this is that there's a certain size in which the precipitates are the most effective at strengthening. And if you grow your, if these precipitates, they grow with temperature. You know, time, temperature, these things will actually begin to grow. If they get too big, they don't strengthen as well. So you take a material like a 6000 series aluminum, and then you heat this material up, all the atoms start moving around a lot, and you get a solid solution. You quench it, still a solid solution, but it's frozen out at a lower temperature. And then as you start heating this material up, the precipitates will begin to grow, kind of like raisins in bread, let's say. They'll begin to grow in the material, okay? And they'll keep growing the longer you heat them, okay? The higher the temperature, the size they grow to is the function of those two variables, the time and the temperature. They can get too big, like I mentioned, and then they don't work as well. And I can explain why that is. We talked about this guy right here. This is when the precipitates are small enough and a dislocation is moving towards a precipitate in the material. So by the way, the precipitate could be like a metal carbide, for example, like we call them M2C. So M is metal, C is carbon, so M2C, so two metal atoms to each carbon atom. Right? That's an example of a precipitate. The ones that are in aluminum, I think, are some kind of aluminum silicide sometimes, or aluminum silicide magnesium, or magnesium together. Anyway, so when these dislocations are small and a dislocation is moving towards them while the material is being deformed, once they get to the precipitate, it's energetically favorable for the dislocation to actually cut the precipitate in half. If the precipitates are big, it's energetically favorable for the dislocation to what's called loop around the precipitate. And this is what that actually looks like under transmission electron microscope. Okay, there is an optimum. So once you get to the point where they're looping around the precipitate, then the increase in strength is decreased. The bigger the particles get, the more looping, the strength of the material goes down. So there's an optimum size where you're growing these tiny little precipitates, a couple nanometers, getting a little bit bigger, and they hit a point where, where they're the exact right size that they're causing the most difficulty for the dislocation to cut through them. See that? So this point right here, this point where you strengthen.
I have a question about that with the precipitate size. Why
Yeah.
is that when I have bigger precipitates, they loop around? Because in my mind, if I have a big precipitate and the dislocation comes, it has to bend a lot more to come all the way around it. So it would be way harder for it to kind of loop around.
You say it's like a surface area,
Yeah, rather than just cut through it. So in my mind, I would have expected
the opposite.
Yeah.
What's your name?
Julian.
Julian. I see your logic, and it does make sense to me. But the reality is that when the dislocations get bigger, they loop around. I can't tell you the thermodynamics of it. Professor Shu probably could. I can read up and get back to you next week. But it's an interesting question. You would think that since there's energy associated with this missing column of atoms, that looping them around a precipitate would mean that would be longer, which would mean more energy. But I guess
Would that be balanced by how far they have to cut through though? Like, could that be worse?
it could be, yeah, and the lattice distortion. Amelia?
Oh, yeah, actually, I have a second question.
Yeah. Okay, real quick, just want to make sure that everyone understands this. As these precipitates get bigger, it takes more energy to get a dislocation to cut through them. And that's an increase in strength. There's a point where they get so big that whatever thermodynamic reason, Julian, they wrap around. Okay, and then as that happens, as they get bigger, the strength begins to drop off. And then the point where you're getting most strengthening the precipitates is some critical size. I can't tell you what that is off the top of my head, but it's probably different for different materials.
I think my understanding is
Tyler, right, okay.
bending precipitation to a very tight radius has a very high energy penalty. So the
Me too.
larger the precipitate is, easier it is. It's like not recalling itself. as
Yeah.
much.
That makes sense. You like that explanation, Julian? It makes sense to me. But the thing about it is all these things have some quantity of energy associated with them, right? And more or less, together, not together, it's difficult to really, I think, figure this stuff out as sitting here. I think that's why some of the computational tools are so important, because these tools have the capability to run a bunch of different scenarios and determine why this happened. The trying to remember, it's Lifshitz and someone else is the people who wrote Lifshitz and Wagner. They wrote them. They wrote a model about this, I think, back in the 70s, trying to predict what would happen. Which would be more thermodynamically favorable, cutting or wrapping, looping, and what that translates to in terms of strength. But it's a good question. I'll look up on that. Get back to you guys next week. Okay. Deal. Okay. Amelia, what's up?
So all of this is happening when, like, you have your material, like you're trying to bend some material, and so that's when dislocations are going to be running through. And then, so our goal with the precipitate stuff is to slow down the dislocations as much as possible. Okay.
I think you got it. It's if you take it's classic. You take a piece of metal, and probably Robin, you know about this more than I will maybe. If you take a piece of metal and you're stretching this piece of metal, you can actually resolve the stresses to a shear stress. The shear stress is what moves the dislocation, right? So that's what you're thinking of these planes sliding past one another. Okay, so you're bending this material, you're bending this material, you're bending this material. The dislocations are moving through on planes that are under shear loading. So it's not all the planes in the lattice or all the crystals and all the grains. They're moving across each other. They're moving across each other. And then at some point, they hit one of these precipitates, or they hit the stress field around the precipitate. And then it takes more and more energy to get the atoms to slide past one another. And if you resolve that point, it's taking more energy to get these little dislocations, these little planes to slip past each other. On the macro scale, that's an increase in strength. Does that make sense? Okay, good.
Awesome. Thank you.
Yeah. Right. Okay, so that's precipitation strength. All right. We yesterday, I gave an example about a part that I was responsible for that was an aluminum housing for an electric motor. And the way they were making this thing is they would heat up the aluminum housing, they would drop the motor into it, and then let it cool down so that there was an interference fit between the two, so the motor wouldn't slip relative to the aluminum housing. And they were heating this thing, and I think it was some like 300 or 400 degrees Celsius in a furnace. And if they had just left it there for a couple of minutes, it probably would have been fine. But the problem is in the actual factory environment, they were leaving this aluminum housing in a furnace for like 6 hours. And so they would get the motor installed in the aluminum housing. We would get the part back at the company I was working at. We would test them and they would fail. The aluminum would burst into zillion little pieces. And the reason for that was that they had overaged. They had coarsened the precipitates to the point where they weren't strengthening effectively. So the finite element analysis said, okay, there's, the stress here is 20 KSI, no problem. This material's got a strength of 40 KSI if it's heat treated properly. Turns out it wasn't heat treated properly, it was overaged. And it might have had a yield strength of 15 KSI. So that when it saw the 20 KSI from actual surface load, it failed in a million pieces. So the reason I bring up that story is just to always remind you that if you ever get involved with something like this in manufacturing real parts, always go to your manufacturing site and watch what they're doing. Talk to the people on the line who are building these things and ask them what they're doing. Because that's how I figured this out. I went to this plant that actually was the one near Blacksburg. That was that trip. And that company was Aspen. I was like, probably should protect them. I didn't say that, guys. So this company was Aspen, and they had these things in this furnace for 6 hours, and like we couldn't figure out why they were failing. These guys even had metallurgists on staff, and I'm going to these guys, why is this thing failing? You know, we took hardness tests, and we determined it was much softer than it was supposed to be. They wouldn't tell me what was going on. I went down the line and I sat there in a corner and watched them do things. And I saw them put the aluminum housings in this furnace, and then like I said, like, you know, I walked up to the line worker, like, how long do they stay in there? She's, oh, well, sometimes, you know, we got an 8-hour shift. Sometimes they stay in there for 6 hours. Well, that was more than enough time to soften the material substantially and cause a failure. So always stand on the factory floor and watch what they're doing. Problems up.
How do you know how long it can be at that temperature without it degrading? Because like
Right.
with heat treating aluminum, just welding is enough.
Absolutely, because the temperatures are much higher than 300 degrees Celsius. How do you know? In the old days, they would do studies where they would maybe take a bunch of cross sections. Okay, they would heat them all up, and they would mount, polish, etch. They would look at the precipitate size, and they would know they got above a certain size. Or they would do studies where they measured the hardness, even the strength, as a function of temperature and exposure time. So it was done by trial and error long ago. Now the cool thing is today they actually have models that can predict these things. So a program I'll talk about, I think we'll get there today maybe. It's called Thermocalc. It was developed in Sweden. I guess there's been incredible work done, I guess in some university there where they worked on a lot of thermochemical databases. They you know, just would sit there for hours and hours, I guess, just calculating out these, you know, enthalpies and things of these materials, all these different materials combinations. Incredibly laborious, miserable work that they must have assigned to some poor graduate student. And then they wrote the Thermocalc program, which expanded on the work by Kaufman and Cohen to predict phase diagrams, right? So this software has advanced a lot over the past 20, 30 years. And I think I'm pretty sure there are ways within Thermocalc where you can input a composition of a material, and then you can expose it to temperature for a certain amount of time, and it'll tell you what the precipitate size is. And then there are models that will correlate the precipitate size to the strength of the material. Right, Schwarzschild, that was it. The Schwarzschild theory is the one that correlates between precipitate size and strength. So I think this is a really interesting time right now in the world of material science because computers are getting so fast and so cheap, and these atomistic models that try to predict strength or phases, they fill in the processing structure link and the structure property link. They predict those things, and they're getting better and better at it. And this is all being driven by, you know, experience, trial and error, a lot of hardworking grad students, and really cheap, high-powered computers. It's really an interesting time. What's going on now with all that? You guys, I mean, you're in the material science department, right? Julian, I mean, you must know about this. Yeah. Another way to strengthen materials is called Hall-Petch strengthening. And Hall-Petch says that the strength of the material, or the increased strength of the material, is inversely proportional to the square root of the grain size. So the smaller the grains, the stronger the material. This is a real effect. I've actually played with this one myself. So you guys know Professor Shu in the material science department. Some of you probably know him. So Professor Shu started a company called Extalic. And Extalic was, well, what they do is they make nanocrystalline coatings. And these nanocrystalline coatings are made out of nickel and tungsten. And they're incredibly strong. Much stronger than a nickel, a pure nickel would be, for example. And so this is a real effect. And I think this has the reason this works is that you have dislocations that are inside the grains. It takes more energy to get a dislocation to traverse a grain boundary than it does just to go through a grain. So you have many more grain boundaries because the grain size is smaller. Then you can slow down, you can make it that much more difficult because the dislocations have to jump over more grain boundaries, right? And that's more energy, that's higher strength. But you got to be careful with this one because the size of grains will grow with temperature and time because a lot of energy associated with having all that surface area, with all those grain boundaries. When I was a graduate student, there was a friend of mine, and he was working in the lab of Julie Wortman, who was very famous in the dislocation world. So was her husband, Hans Wortman. He unfortunately died about 2 years ago. Anyway, they had, my friend was Brian, and he was working on a nanocrystal in nickel. And they made this nickel by heating up the nickel. Okay, so all the atoms are flying around in a vacuum, and they would stick in a cold finger that was chilled with liquid nitrogen, and the little tiny pieces of nickel bubbles basically that were flying around would solidify on this little cold finger. They would solidify to make these nanometer-sized little crystals. They would then consolidate. My friend Brian would actually consolidate these crystals into a little tiny thimble of nickel, literally like a little tiny nickel. Okay, little tiny thimble of nickel, of nanocrystal nickel, and he was able to prove that the strength was 5 times as high as a normal nickel. And then, I don't remember what his grain sizes were, but they were definitely, sub 100 nanometers. So this is a real fact. Now the problem is that on Monday he had 5 times the strength. On Friday he had the normal strength of nickel. Does anyone know why that happened? Julian, you must have. So on Monday he had 5 times the strength of nickel. On Friday he had 1 times the strength of nickel. Lucas?
Grain growth?
Tyler, grain growth, exactly. So grain boundaries represent energy, right? Grain boundary energy. You probably will hear that a lot. Material systems as well, change themselves to minimize the amount of energy, like everything else, right? So what happens is these materials, the grains would grow, you get diffusion, the grains would grow, and you would end up with normal microcrystalline grains rather than nanocrystalline grains, and the material wasn't strong anymore. Okay, now Chris Hsu had this problem went on for like a decade, maybe 2 decades that I can think of. When I was an undergraduate, I worked in a lab at UC Irvine, and they were making nanocrystalline aluminum, and they had the same problem. So this problem with the drop in strength with grain size increase. This is a problem for like a decade, 2 decades maybe. And I'm not sure who the first to solve it was, but I know Chris Hsu solved it by finding a way to what he calls paint the little grains, the little nickel grains, in his case with tungsten. So you can kind of imagine like a malt ball. You guys eat malt balls? You got the malt in the center, you got the chocolate on the outside. It's the same thing. The center of the malt ball was nickel, and then the tungsten was the chocolate on the outside. Okay, and because of the thermodynamics of the tungsten on the surface, he made it so it was thermodynamically favorable for the system, or at least, well, thermodynamically favorable for the system to keep that grain size. Increasing the grains would increase energy in that case, because the way the energy interface between the nickel and the tungsten, right? So it's almost like the chocolate was some really high surface energy, so it made sense to keep it small. Or I'm sorry, switch that. The chocolate was lower surface energy, so it made sense to keep the malt ball small. The effect is still fleeting to some extent, because if you heat those materials up past like 300 or 400 degrees Celsius, the grains will begin to grow anyway. So a lot of the materials that he produced were only really good for, applications of a surface life up to maybe 200 degrees Celsius would have to worry about grain growth. So Professor Hsu's done a lot with this kind of thing. You could, if you're interested, go look at some of his papers in the library. He's got some good ones. He talks about the energies of the different, chocolate and the malt ball. It's good research. It's really interesting, and I'm sure I don't exactly know what he's working on right now, but I think he's probably gone other places with this and tried this with different material systems to try to build stable, or at least metastable nanocrystalline materials.
Back to this nanocrystalline nickel, so there was diffusion at room temperature within 4 days.
Yeah, that doesn't sound right, does it?
No.
Okay, maybe I misspoke. Sorry, I can't exactly say what it was, but somehow the grains grew. I don't know if it's room temperature diffusion. When I was a graduate student, there was some graduate student came in and started talking about room temperature diffusion, and he got in this big fight with the professors, and there can't be room temperature diffusion. That's not possible. But How do grains grow if there's no room temperature diffusion? Any ideas? I guess it's another question for Professor Eager. I'll ask him. I'm not really sure. Transformation strengthening is another way to strengthen materials. Steel is a really good example of this. So steel, normal steel that you get from the steel mill at room temperature is ferrite, and maybe a little bit of pearlite. And that material is kind of soft, not real strong. If you take that material, that steel, you heat it up to, what is it, like 870 degrees Celsius, you leave it there for about an hour, it goes to austenite. So at room temperature, it's body center cubic. At 870 degrees, it's face center cubic austenite. And then you take that and you quench it. And when you quench it, it locks in that austenitic structure. So it stays FCC. Okay. Part of that will transform to what's called martensite. Martensite is body center tetragonal. And that martensite has this, because of the thermodynamics or whatever, it's got that really tight little needle structure, these kind of interlocking little needles, little tiny nanoscopic little needles that interlock with one another. Call them martensitic laths. It's another subsystem of the microstructure. They're very strong. It's very hard to get a crack to propagate through that stuff, or dislocation to move through it. And so there's an example where you've gone from ferrite to austenite to martensite, and the martensite is much stronger than the ferrite. There's an example of phase transformation strength. Composite materials. Okay, carbon fiber is lovely stuff. It's nice because even as an undergraduate working in a maker lab somewhere at MIT, you can laminate your own carbon fiber parts if you're so motivated and make little parts out of this. Carbon fibers themselves are incredibly strong and incredibly stiff. And fortunately, they're just really small and wiggly, so you can't do a lot with them unless you embed them in epoxy or some other polymer resin. Okay, the resin serves to transfer load from the outside boundary to the fibers, so all the loading goes on the fibers. Very little bit goes onto the actual epoxy. The epoxy or whatever the matrix is, the polymer matrix isn't that strong. But if you can effectively get the load onto the fibers, you can make materials that are incredibly stiff and incredibly strong at room temperature, or maybe a little bit above room temperature. Those types of materials aren't really necessarily good for, I don't know, airframe components that see 2000 degrees Celsius. The matrix would burn off. So that's another strengthening mechanism. So what I've given you here is a variety of different strengthening mechanisms. Most of these are for metals, granted. The composites, that could be metal, that could be ceramic, that could be polymer. So these are microstructural systems and subsystems that a materials engineer has at their disposal to increase the strength of a material. Right? The next question is how do we get those? So we're going to talk now about the processing to structure link. Okay. Steel. We just talked about steel. Take a piece of steel that might be fresh from the mill or something, and you heat it up to 870 degrees, and it turns to austenite. You quench it down to room temperature or somewhere about there, and most of it will transform to martensite. Some of it will stay austenite, which actually can be useful in some cases. But you transform it to martensite, and the martensite is much stronger. Martensite can be brittle, right? If it's too tight. So there's such thing as called tempered martensite. So you may take that material after you've quenched it and heat it up again, which will grow the martensite little laths a little bit bigger, so they're a little bit more forgiving when they see a crack. They don't split apart and become a brittle material. They stay ductile. All right. So that's an example of filling in the property of structure link. One example, okay? Here's another example. This one's going to be a little more confusing. And we got 6 minutes left. Let me try to explain this one. Okay, you have steel. The steel has a bunch of interesting elements in it. Chromium, tungsten, molybdenum. This one is chromium and molybdenum. Vanadium, nickel. The really high strength steels that they use for like airplane landing gear, and gears in your car, and some really high end bicycle parts. Are these high alloy steels, or these alloy steels, right? And it turns out that when you mix all this stuff together and you do this heat treatment that I just described, you austenize, quench, temper the martensite that you get, so it's not quite as brittle. Then there's other treatments you can do that will grow precipitates depending on the alloy concentration of the material. They grow different types of precipitates. And if you've ever used Thermocalc, has anyone ever used Thermocalc in here? Julian, have you used it? Use it too? Okay. Thermocalc, when you say, okay, I want to mix these 7 elements of materials together, and you press the go button, basically, it'll give you a list sometimes of like 20 or 30 different possible phases that'll form. A precipitate is a phase, right? So sometimes there are, for example, like carbides are very effective at strengthening metals. Some carbides, not all carbides, some carbides are. So when you have 6 metals around next to a carbon, an M6C carbide precipitate, apparently those will deteriorate the strength of a metal. It has to do with corrosion, but I don't want to get too far into that. When you have an M2C carbide, so 2 metal atoms of 1 carbon, those can be very, very effective at strengthening a metal. They do the best job at strengthening when they're really small and there's lots of them throughout the whole material. So they call that a fine dispersion of precipitates. Okay? They can grow and they can get soft again, but let's just say for now that they're just going to stay well dispersed and they're going to be tiny. What's called the thermodynamic driving force is what determines the size of these precipitates once they start to form. So at certain thermodynamic conditions, you'll get a few of them that are big. Okay, if the thermodynamic driving force is low, you get these big ugly precipitates that don't do that good of strengthening because they're overcoursing. If the driving force, thermodynamic driving force, to get these precipitates is high, then you get the fine dispersion of these precipitates, little tiny suckers growing in it, maybe only a couple nanometers wide, right? So Thermocalc will actually tell you what the thermodynamic driving force is for various different phases that are going to form in the material. So this, you guys see where this is very, very powerful all of a sudden? You look for phases that have a high driving force. You look for the alloy composition and the temperatures that maximize the driving force to precipitate out these little particles. Because you know that if you get a bunch of these things, little tiny pieces all over the place, you're going to have the biggest increase in strength. So here we are again, we're designing the material. We're picking temperatures, we're picking compositions that maximize this thermodynamic driving force to form M2C carbides over, say, M6C carbides, right? This has to do, the other thing that affects the strengthening effect from a precipitate is whether it's, they call it coherent or incoherent. So coherent means that the atomic planes of the precipitate line up with the atomic planes in the lattice of the material. Incoherent means that it's just like a little piece of material sticking there. The atomic planes don't line up. It's like a little, it's like barely even connected, just a thing that's almost even shaking around. Those are not as effective. So they can actually weaken a material rather than strengthen it. So here we have two graphs that I copied out of Greg Olson's work. I redrew them, but they're actually his work. Originally, these were directly out of Thermocalc, but I just redrew them in PowerPoint because they're easier to read. And this is a graph of weight % chromium versus weight % molybdenum. So choosing how much molybdenum, how much chromium you're going to put in your steel, what's going to give you the highest strength. You want to choose these compositions so that you maximize the driving force for making M2C carbides and minimize the driving force for forming incoherent M6C carbides. Make sense? You guys want to take a second to breathe that in, or? Okay. This, you guys got that? Not seeing many shaking heads, huh? Okay, try it again.
Yeah.
Okay, so there's coherent precipitates and incoherent precipitates. Coherent ones means that the atomic planes line up. Incoherent means that they don't. It's almost like a little ball sticking in there that isn't really attached to all the stuff around it. Okay? The M6C carbides are incoherent. There's also some corrosion things there that I think happen at a really small level. The M2C carbides are coherent. In order to get preferentially one over the other, you pick the one that has the higher driving force. And then you want to maximize that driving force in order to try to form this finest dispersion of these precipitates. Okay, so here we've got these two graphs. One of these is the drive, it's a contour plot for M2C carbides. That's this one here in blue, and then the green one. That is the driving force for the M6C. Okay, this yellow dotted line right here, those are the stoichiometric, the correct stoichiometric, what do I say here, ratio for the material, so that these are the compositions you can actually get. You can mix these different amounts of these atoms together into the steel, and you can get something along this line. Right? You can't really deviate from this line. You really have to be on this line because of stoichiometric reasons. Okay, so if you look over here, you think about how you're changing the composition here. At some point, I think it was 15 kilojoules per mole. You start to have corrosion problems because of the material that's forming in here. There's like a galvanic couple, maybe, and read some more on this. Okay, so you know that you can't really go beyond, you can't go for less than 1% molybdenum and more than about 1.9% molybdenum, somewhere right about there, right? So you're on this line. Then you want to find the highest value of the driving force for the M2C carbides. So you want to find the point, the composition that's closest to one of the, say, like peaks or tangents of the highest line you can get to. And that's right about here. So that translates to a composition that's right about there. Okay, this won't really work. This one will because of the stoichiometry. So you figure out that this is the optimum percentage to maximize the driving force for the M2C carbide, right? Because you're thinking you're moving this direction. Okay, you can't be down here because you can't go past 15 on this side. So sorry, you're moving this way in the line. You can't go past 15 because then you start having corrosion problems. Okay, so where can you go? Where can you get the highest driving force for the M2C carbides? And that's this line right here that says 19. Okay, so you're somewhere right in here. This is the composition that will give you the best finest dispersion of these M2C carbides. Does that make sense? Amelia, you look stressed out.
Yeah. I guess I don't understand why, if one of these is for incoherent precipitous and one of them is for coherent precipitous, I don't understand the motivation for bringing the green line that corresponds to 15 into the coherent.
Because if you know that if you run into some composition that's past this 15, remember this is getting bigger, these driving forces going that way. If you go past this 15, then you know you've got corrosion problems. So you know you can move down this line and only go to here. And then so now you're on this green line. The question is, where do you go up and down to get to the highest point on the mountain for the driving force for the M2C carbide, which is right here.
But I thought you said that the corrosion problems only kicked in for incoherent.
That's right.
So if we're looking at, so how would we assume that corrosion problems kick in at 15 for coherent?
Okay, let me try again. So you know from experiments that the 15, the precipitates you get at a 15 kilojoule per mole driving force will give you corrosion problems and higher. You can't go further down this way. Okay, so you're stuck. This 15 is furthest you can go that way with molybdenum. So you're going here. Okay, so you're moving down the line and you're saying, where can I get to? You know, how close can I get to this 19 line? Because that's the highest driving force for the M2C carbides. And that composition is right in here. I probably should move this down a bit. So you can't go higher than 15 here because you've got corrosion problems. But you want to go as high as you can that way. So you get the highest driving force for the M2C carbides. So that point is where this lobe turns over on the 19 kilojoules per mole contour.
Okay, I think I understand that more. I guess I was confused with all of these were we were considering two separate cases, like, oh, what if it's incoherent, what if it's coherent?
Right.
Okay.
They always exist. like the missing material, because I need it missing. thing.
Yeah, I mean, you want to minimize the driving force for the M6C carbide. So you want to be this direction of the 15 line. Okay, at the same time, you want to maximize the driving force for the M2C, which you want to go this way.
I just meant, like, you're looking at one material that's just forming in two different ways.
Well, if you think of this as you're mixing different materials, you're mixing a bunch of iron atoms and tungsten, iron atoms and molybdenum and chromium. You're mixing these together, trying to figure this out. So this, one thing you should see from this for sure is that when you talk about computational materials engineering, if you try to figure this out by mixing materials in a lab, that takes forever. And to be able to do this so quickly on a computer is really advantageous, and that really will accelerate the development of new structural materials, for sure. It happened already. Okay, great. I think we're out of time, unfortunately. If you guys want to keep talking, that's fine. Let me just turn this off, though. Tim, Christian, do you guys have any questions?
Not today, thank you.
You good?
No,
Yep.
all good. Thanks so much.
Okay, bye.
Take care.
Bye.